So knowing what Newton's first, second and third laws are is really important for a physicist. For anybody who just needs to understand how to use forces, it doesn't matter if you know which law is which, but you do have to understand the effects. Lots of people hugely misunderstand forces, and when you're dealing with that as your career, that can actually be really, really dangerous if you're giving somebody the wrong advice or misunderstanding the way a situation works. So let's have a look at each of the laws in turn. For Newton's first law, what it basically states is that an object will remain in motion unless a resultant force acts upon it. So to start with, let's just have a quick look at what the hell we mean by a resultant force. So in this object, we've got a 2 Newton force pulling to the left, a 4 Newton force to the right. The resultant force is kind of once they've balanced, it's the overall effect. So 2 newtons to the left, 4 newtons to the right. Once you kind of add those or cancel them out, what you've got is a 2 Newton force to the right. So this object, this ball, would ultimately accelerate to the right. So objects keep the same velocity unless a resultant force acts on them. Now, a lot of people assume that means there's no forces acting on it, which is the first misconception. And the second problem is they think that if there's no forces acting on it, it will stay still. That's the second misconception. This ball is stationary. This doesn't mean there's no forces acting on it. There is, of course, the force of weight. And if that was the only force, it would now be accelerating downwards. So we've got the floor, which is also pushing up, which is a normal reaction force or normal contact force. Two different names for the same thing. These two forces would be the same size, so the resultant force on this ball is 0. That doesn't mean it stays still. It just means it carries on doing what it's doing. Constant velocity. If the velocity is 0 because it's staying still, then that's fine. That's what it'll carry on doing. But in this example, this object is being pushed forwards, Fa, but is experiencing friction, F1, to the left. The two forces are balanced, but the object is going to keep moving. The resultant force here is 0. So it's moving at a constant velocity, and it keeps moving at that velocity as long as the resultant force is 0. The common misconception is that you keep pushing something to make it keep moving, and actually you don't need to. You push it to overcome the friction, because if you don't, the friction will stop it from moving. If this person stopped pushing this box forwards, the only force on it would be the blue arrow backwards, and that would cause it to decelerate and stop. So the only reason you are pushing it is not to keep it moving as such, but to cancel out the friction, and then it will carry on moving by itself. I know, 6 of one, half a dozen of the other, but really that you've got to understand what it's coming down to. This is why it takes more force to start something moving, because then you're overcoming friction and doing a bit of acceleration. Once it is moving, it doesn't quite take as much force to keep it moving. It's also down to the way that friction works, but let's not get too deep into those details now. So we also need to understand the idea of inertia. So Newton's first law is really about the idea of inertia, and inertia is effectively the same as mass. Inertia is about how difficult it is to make an object start or stop moving. So firstly, don't get this confused with the momentum. Inertia and momentum are two different things, but they're often used as if they're interchangeable. They are different things. An object that's moving has momentum. An object that's moving faster has more momentum. But an object's inertia just depends on how much mass there is. So basically, a shopping trolley that's full of tins of food will be very difficult to push and get it to move in the first place. And once it's moving and it's careering down Tesco shopping aisle and it's about to slam into some poor person who's not paying attention, and somebody tries to stop it from moving, it's very difficult. Do the same thing with an empty shopping trolley. The inertia of that is a lot lower. It's much easier to start or stop the motion of the empty trolley. It's got less mass in it. So inertia is really the idea behind the first law, but where practically this can be considered is, for example, in a car. So in this example, this stupid example, the car stops, but the giraffe's head wants to keep moving forwards. Remember, objects will carry on at the same velocity unless a force acts on them. So why does the giraffe's head actually in the end stop? Well, because it's attached to their neck, and their neck is attached to their torso, which is strapped to the car through the seatbelt. The head wants to carry on moving. The thing that stops the head from moving is the neck and the neck muscles. Now, this is a bit of an extreme example using a giraffe, but it does demonstrate, for example, why people get whiplash. When they're in a car, the car stops suddenly, they're wearing their seatbelt, the seatbelt stops the torso, but there's nothing attached to the head to stop the head other than your neck. So your head keeps moving forwards until something stops it, which is the neck muscles. And if that's strong enough force, the muscles down the back of the neck can rip, and that's what causes whiplash. That might make it sound like that's a case for not wearing a seatbelt, but what you've got to consider is what would stop you or your head or any part of your body if you weren't wearing the seatbelt. And the answer is the steering wheel, dashboard, or windscreen. So that's definitely less good. Whiplash is certainly a lesser injury of the two possibilities. But it does show you the idea of Newton's first law, often misunderstood.